Assalamualaikum and very good morning. So we are going to continue for chapter 4, which is on the discrete time Fourier transform. Okay, if you look at what you have learned in chapter 3 last time, we have learned about the discrete time Fourier series pair. So basically Fourier series is used for the periodic signal. So if you see here that you have the equation for Fourier series, so let's jump directly to the Fourier transform equation. So we have two equations for the discrete time Fourier transform. First one is the Fourier transform and second one is the inverse Fourier transform for discrete time. So if you see here that you are given for both the equation is that when you are given signal xn, find x e to omega which is in the frequency domain. So let's say that if you have a signal, so you can either use two ways, either to use Fourier series or Fourier transform. So normally if you have a periodic signal, you are going to use Fourier series, and for aperiodic signal is that you are going to use Fourier transform. So right now when we calculate is that we use this equation. So x e j omega is equivalent to summation of minus infinity to infinity. Xn means that this xn value substitute here e minus j omega. So we have the first equation. Second equation is that when you find the equation for the signal x in terms of frequency domain x e j omega, so you wish to find what is the inverse Fourier transform for signal x. So therefore we are going to use this equation. So xn equivalent to 1 over 2 pi integrated 2 pi x e j omega. So means that this signal we are going to substitute here e j omega d omega. Okay, so this is the two equations that you are going to use for the discrete time Fourier transform pair. So let's look at the example, which is example 10. So you are going to consider the signal below. We have given xn equivalent to a n u n. So if you see here, a n is actually a step input signal. So find the discrete time Fourier transform of xn, where un is a step function. Okay, so how to actually solve for this example is that read carefully the question. So you're given signal in terms of the continuous time, in term of time domain. So you are asked to find or calculate for the signal x in terms of frequency domain. So you're going to use this equation x e j omega equivalent to summation of minus infinity to infinity x n value e minus j omega n. Okay, so let's look at this solution. So we have the equation here. So substitute in this first equation, general equation. So this is the general equation that I give to you. Okay, so substitute that and you have the value xn here. So xn you're going to substitute in this first equation. So xn equivalent to an un, but however un, you know that it's a step input function, so means that it's a step input function from 0 we have a value 1 until infinity. Okay, so meaning that you can actually this value you can omit, so it's equal to 1 and e minus j omega. Okay, and if you look at this is that if you look at this equation, you have the step input function is from 0 until infinity. So therefore that's why you have the 0 until infinity here. Okay, you do not put it minus infinity. So 0 into infinity, and this one you just group it together, so you get summation of 0 to infinity a e minus j omega n. Okay, based on this, write it out. Okay, get the summation value, then you will get 1 over 1 minus a e minus j omega. Okay, or you may refer to the discrete time Fourier transform table. So if the table you look at this is given by a n u n, so you have a n u n and you will get the equation similar to this one. So basically this one is like a proofing for the equation a n u n. So we are going to look at another example. So let's say that you have the signal here given by xn equivalent to a modular n un. So un is the step input signal, so an is given by xn is given by the signal. So find the discrete time Fourier transform of xn. Okay, so let's look at how we are going to solve this problem. So you have you're going to use the general equation here. Okay, so general equation, start with that, and then substitute xn value into this xn value. So you have a modular n e minus j omega. Okay, and then since if you see here for this signal here, you see that you have the positive and negative parts, so meaning that you are going to actually divide it into from 0 to infinity and from minus 1 until minus infinity when you want to do the summation part. So we are going to separate it into two parts here. Okay, so summation of from 0 to infinity is a n e minus j omega n plus from minus sorry, this is reverse, so minus infinity to minus 1. Okay, a minus n e minus j omega n. So so for that, then you will get a e minus j omega n plus summation of 1 to, since we are going to change the value for minus n here, so let's say that you have m equal to minus n. So for this first term here, you're going to use the value n. For the second term, in this term, we are going to use the value m. So therefore, when you have m equal to minus n, then this will become positive, and this m will become from minus 1 become from minus n become m equal to 1 to infinity. Okay, so you have a e j omega m. So solve for the for this equation, then you will get this value 1 over 1 minus a e minus j omega plus a e j omega over 1 minus a e j omega. So the first equation here is called the open form, and when you combine it, solve for it, then you will get the closed form value. Let's look at another, for this exercise is that try to do it at home. So consider the rectangular pulse. So you have the value for n minus 1, the modular, for value 0, for smaller than n1, so you have n1 and n minus 1 here. So larger than the modular is equal to 0, so that's why you have the 0 part here. Okay, and other than that, you have value 1, so you have 1. So try solve for this equation when you have n equal to 2. So this one n equal to 2, so basically we have 0, minus 1, sorry, 0, 1 and 2, and 0, minus 1 and minus 2. So try to find what is the j x e j omega value there. So this one is the first exercise for this session. Next, we are going to go for the inverse Fourier transform. So like you have learned in Fourier series, when you converted the signal from time domain to frequency domain, you like to actually convert it back to the original signal in terms of time domain. So this is what we call as the inverse Fourier transform. Okay, so let's look at example 12. So let's say that you have xn equal to delta n. So in this case is that the analysis, if you refer to the table of equation, for the discrete time Fourier transform, look at xn, so you will actually get the value for x e j omega equal to 1. So in other words is that, okay, this delta n can be represented as 1 in terms of frequency domain. However, we try to solve for this equation by deriving it. So let's see how we can actually solve this problem. So let's say that we have x e j omega equal to 1. So we have the value, this is the general equation. So we have 1 over 2 pi from minus omega to omega, x e j omega e j omega n d omega. So you have what is the value for the signal xn just now. It's the value is 1. So substitute into this value 1. Therefore, you get integration for 1 e j omega n d omega, and then try to integrate it. You will get the value this in terms of 1 over 2 pi j n e j omega n minus e j omega. So if you look at this one, is that you can actually convert it into the sign value. So you have, finally you have omega n equal to 1 part over pi n sin omega n. So this one is actually representing the delta signal. Okay, this is just to look at the property of the discrete time Fourier transform. So this one, look at the appendix that for the table, Fourier transform table. So there are few appendix, so I will show to you in the next table. Okay, this is the basic discrete time Fourier transform pair. So if you see here, this is the signal over here, then you have the Fourier transform. Okay, so example is that example that we go to, that we are equation, that signal that we are going to use normally is the signal an un, and then also the signal un here, and even the shifting property we have delta n minus n naught, so and then the delta n. Okay, so this one is really useful. And also you might be using the property of the discrete time Fourier transform. So you have the nullarity here. Okay, and okay, just go through. There are two tables for the discrete time Fourier transform, right? Okay, now let's go to the convolution of the discrete time Fourier transform. Okay, if you remember in chapter 2, you did the convolution in time domain. Okay, so similarly, if you see here, for this one is in time domain, this is in the frequency domain. So similarly, in the using Fourier transform, you can actually calculate for the output value using the frequency transform. Okay, so let's look at an example. Consider an LTI system with impulse response. So you have h n equal to delta n minus n naught. So means that if you see here that you have two different property of the signal. The first one is actually the impulse signal delta n, and we have the time shifting here. So there are two properties. Okay, the question is that find the frequency response h e j omega if given the input x e j omega. Okay, so alright, so to solve this problem is that like I said, we have two property here, delta n and the shifting property. So to solve that, let's look at the solution. So first of all is that for the h n value, the question was to calculate the frequency response for h e j omega. So if you look at the block diagram here, you have the frequency response here, you have the output y e j omega and the input. So therefore you can calculate for y e j omega, h equivalent to h dot x. So we going to actually calculate for h e j omega first, so which is from here. Okay, so using the general equation, okay, substitute it inside here, and then hn value, okay, this hn value, substitute it here. Okay, so you will get delta n minus n naught e minus j omega n. Okay, and then to look at this, to solve for this is that you need to refer to the Fourier table property, Fourier transform table property. So first of all is that look at delta n. Delta n, if you refer to that, you will get the property in the answer is 1, and for x n minus n naught is e minus j omega naught. So therefore you can rewrite this to delta n is delta n here, and x n minus n naught, this one is written as e minus j omega n naught. Okay, this one. So delta n, just now you have 1, value 1, so therefore you have the final answer is this one. Okay, you haven't solved yet the equation. So next is that solve for y output, y e j omega. So y e j omega is equivalent to h e j omega dot x. So e, you just take this value, substitute here, dot x e j omega. Of course, for this example is that for the x e j omega value, you don't have any signal. So later on in the next example, we are going to give you a signal, then you are going to calculate for the output in terms of frequency domain. Okay, and if you see here, this one is a table normally used. So this is actually pick up from this table. So delta n is 1 and delta n minus n naught is e minus j omega n naught. Next, let's look at example 14. So example 14 is consider an LTI system with impulse response given hn equal to 0.5 n un and given the input to the system xn equivalent to 0.2 power n un. So find y. Okay, so means that you actually are given hn and sn. So you are given hn and xn, so find y. Okay, so yn, we can just write it out. Yn equivalent to hn dot xn. You are given these two, so let's try to use the discrete time Fourier transform to convert it to the frequency domain. So hn equal to 0.5 un. Okay, how to solve it is directly refer to the discrete time Fourier transform table. Okay, so look at this table. So you have this one a. Okay, sorry, I missed n here. Okay, a and un. So a is 0.5. So you can actually get the Fourier transform for this signal. You will get 1 minus a e minus j omega. So you write it as for signal h e j omega is 1 minus 0.5 because y or a is 0.5 e minus j omega, right? And for this case is that for the case of Fourier transform, I normally try to use in terms of the Laplace, so because it's much more easier to compute later on. So assume that e minus j omega is equivalent to s. So change everything to s value. So means that 1 over 1 minus 0.5 s. But if you see here is that when you convert it to s, I prefer not to actually have this value a value in terms of point form. So I would like in terms of one integral only. So means that I'm going to multiply by minus 2 over 2 for this both side. Then you will get minus 2 over minus 2 plus s. Rearrange it, then you get minus 2 over s minus 2. So first equation done. Next, we are going to convert x and value. So you get x e j omega. So look at this. What is the a value? A is 0.2. So 1 over 1 minus 0.2 e minus j omega. So like what you have done for the h signal h. So we are going to substitute e minus j omega equal to s here. Okay. So so I substitute here equivalent to s. But I would like to actually leave this with only integer, not in point form. So we are going to multiply it by minus 5 over minus 5. So you will get for signal x e j omega is minus 5 over minus 5 plus s. Rearrange it, then you will get minus 5 over s minus 5. Okay. So well, this is table. This one is similar table. This one is just I just took from the Fourier transform table. Okay, now we are going to solve for yn here. So yn. So you already know that y e j omega is equivalent to h e j omega dot x e j omega. So just substitute value that you get in previous slide. So h you get minus 2 over s minus 2 times minus 5 over s minus 5. Okay, then you will get 10 over s minus 2 multiplied s minus 5. So from here is that you are going to do the partial fraction. So find the value for a and b. So when you substitute it, you calculate it, you will get a value is minus 10 over 3 and minus 10 over 3 and tan over 3. So try to do is this in a piece of paper. How do you get A and B here? Okay, using the same method like what you have learned in chapter in the previous continuous time Fourier transform. Then we are going to substitute value for A and B in this. So substitute A and B. Okay, you are going to get this equation. And right now is that we are substituting back again this the S value equivalent to E minus J omega. So substitute back S here and rearrange it. So rearrange it back so that the E minus J omega will be on the right side over here. Okay, so I rearrange it. Instead of the S value on the left side here, I'm going to rearrange it to the right side. Okay, so when you arrange it, you will get in terms of this value. But if you compare it with this table, you will see that you will need to have this value 1, 1 minus alpha E minus J omega. So this value, you see that there's a value here, minus 2 and minus 5. Therefore, for this part here, I'm going to divide by minus 2 over minus 2, and this side is that going to divide it by minus 5 over 5. So when you divide that, you will actually get this equation. Okay, so you get 5 over 3, 1 over 1 minus 1 over 2 E minus J omega. So this if you see the format is similar to this table. Okay, you have in terms of 1 over 1 minus A E J omega. And for the second equation is that you will get in terms of this value minus 2 over 3 and so on. Then using the Fourier, the inverse Fourier transform here, convert it back to the signal yn in time domain. So you just need to convert this back into time domain. Okay, just refer to this and compare it. So you will get the value 1 over 667. Okay, alpha, what's the value alpha here? Alpha is 1 over 2, so 1 over 2 n un minus 2 over 3 is 0 minus 0.67. In bracket, what is alpha here? Alpha here is 1 over 5, so 1 over 5, you have n, missing here, sorry, un. Okay, so this one will be the final answer. Okay, next we are going to look at the system characterization by linear constant coefficient using different equation. So like what you have done in the continuous time Fourier transform, similar to that, discrete time have the same property value. So we are going to try to solve for linear differential equation. So consider the differential equation below. So you are given yn minus ayn minus 1 equal to xn. Find the response of the system in discrete time. So it means that find the response is find h and in discrete time. So if you look at the question here, you have yn minus ay and minus 1 equal to xn. And you see here that this one is actually the shifting property. So shifting property in the inverse Fourier transform, you will notice that for shifting property, okay, you have n minus n naught here, n minus n naught. Okay, so using the discrete time Fourier transform, okay, convert everything to the discrete time Fourier transform. So you have y e j omega minus. So for this time shifting, look back at the time shifting property. Remember in the earlier part of this video, so you have the time shifting property, so which is that a e minus j omega n naught, okay, y e j omega. So this one is the time shifting property. Okay, and for n naught here, n naught value here is actually equal to 1. Okay, so y e j omega equal to x e j omega. So substitute n not equal to 1 inside here, so basically this one will become 1. Okay, rearrange it back, so you have y e j omega in bracket 1 minus a e j omega equal to x e j omega. So the question was to find the recursive response of the system, h e j omega. So h e j omega is actually yn over xn. Okay, so it means that this one you're going to bring it down here, and this one bring it down here. So rearrange that, you will get 1 over 1 minus ae minus j omega. Okay, and after that, the question was to find it in the time domain. Okay, so you need to use the discrete time Fourier transform, the inverse discrete time Fourier transform, to convert back to the time domain hn equivalent to. So compare it with this table. So this table, the time domain is a value an un. So this is the final answer. Okay, so as a homework is that try to solve for exercise 10 here. So exercise 10 is quite similar to what I have explained in the previous example. So just try to convert it into the Fourier transform signal. So y e j omega minus, so you have a time shifting property here. So for this case is that n naught is 1, this one is n naught is 2. Okay, equivalent to 2xn. Okay, so find the response time. Another exercise is that by answering to exercise, sorry, this is not exercise 1 but exercise 10. Okay, so it means that based on this exercise 10, okay, suppose that the input of the system is given by xn, so find the output of the system in discrete time domain. Okay, so you need to submit 3 exercises just now. So that be all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.